Go. So Go isn't still having fun. We can continue having fun, of course. We can also come here. We will have a different kind of fun with Scala. My name is Adam Warski. I come from Warsaw, Poland, and I would like to talk about a bit something different. So we have seen pure functional programming in the first talk, and I would like to show you a bit of impure functional programming. So we will try to take project Loom, which is part of Java 21, and actually use it with the Scala tree, and we will see what comes out. So we are going to take a couple of ingredients. The first one I already mentioned. We are going to use virtual threads, which was introduced in September in the final release. But that's not all. We will also take structured concurrency Java APIs, and we will try to make them a bit more programmer-friendly through an open source project which we are developing to explore what might be a new approach to actually doing concurrent programming on the JVM. We will also take some inspiration from Go. So Go isn't the language that is mostly known for like a lot of conventions in programming languages, right? It's rather taking a very baseline approach as to what kind of features to include. But I think one area where Go really innovated and has shown that a construct is very useful are channels, right? So they are not something that Go invented, they are known from CSP and so on, but Go brought it to the mainstream programming community. So maybe it's something we can actually leverage also in a type-safe and in a more advanced language, at least on the typing side. And of course we will use Scala as well. So let's do an introduction of Loom, because I suppose not everybody might know what Loom is. So what Loom introduces to the JDK, to the JVM, is a notion of virtual threads. So far, in all past Java versions, what we had are only kernel threads, which are called platform threads in the Java nomenclature. So a platform thread is a quite scarce resource. It's quite a heavy resource. It's quite expensive to create, right? So we usually create a small number of platform threads. It's also quite expensive to switch between two running threads in terms of time. So we ended up with a whole, with a very different solutions on how to actually use these kernel threads efficiently. Now in Java 21, what we have are virtual threads. They are very cheap to create and they are very cheap to switch between, right? So here we can see that we are starting 1 million virtual threads. We can try to run this. So you will see that we have started and finished 1 million of these in under a second, and that's on a code JVM, right? So that's quite fast. So what JDK 21 really brings is an asynchronous runtime, which is now built into the JVM, right? So if you have used Effect or Zio, they have implemented a similar thing, an asynchronous runtime, but at the library level, right? And Java brings it downward, depending on how you look. It introduces it at the VM level. It bakes it into the, well, not the language really, but into the VM. So in fact, all JVM-based languages can now use this feature, and we will try to use it as well. So you may wonder, like, okay, great, we have an asynchronous runtime in Effect and Zio. Now it's also in Java. Why should we care at all, right? And I think it's beneficial to actually take a step back and see how we ended up using futures and IOs and so on in the first place, right? The truth is that we have used direct style programming or synchronous programming way back in the past, like maybe 15 years ago or 20 years ago. And for example, when we were doing web applications, we had the thread per request model, right? So each request was getting a thread which processed it from the end to the beginning. But people noticed that this doesn't really scale well, right? And that's because these kernel threads on which this was based are quite expensive, as we mentioned in the beginning. So they came up with various solutions on how to actually improve this situation, right? So first we have callback APIs, which are quite awful to work with. We end up in callback. So then people came up with features which are much nicer. It's a much nicer programming model. Still there are some drawbacks, right? So then we took inspiration from Haskell and introduced the IO monad to our language. But the core reason was actually the core reason of why we are doing that is to efficiently use kernels. So now what happens? Well, we don't really have this original premise, right? We can create as many threads as we want on a JVM, and it's quite fast, it's quite cheap. So is using IOs still beneficial, right? IOs have their price. They have a nice programming model in terms of certain properties, such as you can build pure functions out of them, which enclose side effects. But they also have some downsides, right? The three most often cited ones is first the syntax, which transforms your program into a completely different style, right? You cannot just write statements in your program, you have to program using math and flat-arms and so on. The second thing is that they are viral. So once you have one IO function, you really have to do the IO all the way down, all the way to your main method when you actually run the IO program description. And finally, the stack traces you get from future-based programs or IO-based programs, they are not that great, right? They are often quite meaningless, in fact, because you only get the last invocation from the last platform, but you don't know where this actually came from. And the aim of Loom, they didn't really want to fix it in Scala, they wanted to fix it in Java, but they have the same kind of problems with reactive programming, although they never evolved past futures. So they had the same problems with futures, with asynchronous programming. So the solution for these problems are virtual threads. So the goal of the project that I'm going to show you is to explore are there any benefits left in the purely functional approach that actually make it still beneficial to use it, or maybe we can use synchronous programming once again. And that is the assumption behind the Ox project. It's an open source project which tries to build upon the virtual threads and Scala to deliver a programmer-friendly concurrency API. So let's see how it works in practice. So here we've got two methods which simulate doing some hard work using thread.sleep. We are back in the synchronous land, so doing thread.sleep is completely fine, right? Actually, one important thing that I didn't mention is that Project Loom not only introduces virtual threads to the JVM, but it also retrofits all blocking methods so that they are virtual thread friendly. So sleep, for example, over here, it's a blocking method, right? It blocks the thread on which it runs, but if it runs on a virtual thread, the virtual thread will be blocked instead of the underlying kernel thread. So this is all taken care of. Actually, one more thing which I also forgot to mention is how this works. Maybe you're not familiar with Gets, probably a lot of people are not. So the way virtual threads work in the first place is that you've got a pool of platform threads, a relatively small one, like maybe 10, 15, depending on how many cores you have. And these platform threads are used to run a large number of virtual threads, right? So you run a virtual thread up to a point where it blocks, then you take it off that platform thread and you start another virtual thread, and so on and so on. The same thing happens in the Katz effect, but at the library level. There are the points where the code might switch from one it's called fiber over there, from one fiber to another, are the flat maps and the maps. Here, these are the blocking operations where you can actually switch between threads. Okay, so back to the code. So we've got two methods where we simulate some hardware. And actually at the first approach, so what we will want to do, we will want to run them in parallel, right? Our first approach will be actually to use the Java APIs. These are not final yet in Java, but it's a proposition to include in Java. You can see it's quite long. So what we are doing here is we are using a resource called the structured task scope. And we are forking two computations into the scope. So once you fork, you create a new virtual thread. And these threads, one will run this one, the other one will run this method. Then we have to join the scope, so we have to wait for both forks to complete. We have to propagate errors, and then we can finally call get. And it works. You can see that if we actually run this, it will complete in a little over a second. So you can see that it's about the same time. So they indeed did run in parallel. However, this API is quite low level and it's very fragile. It's very easy to misuse it, right? If, for example, if you mix up the order of these two methods, you will get a... so we've got the stick channel over here, we've got our strings channel. So what we can do in our consuming method is we select from these two channels. That's one of the constructs that's coming from Go. And we either get a tick or we either get a string, right? If we get a tick, we just report on the number of characters received the second. If we get a string, we just add the value here to the accumulator. The important property of select is that it guarantees that it will receive a value from exactly one of the channels, right? You, at first sight, if you have like a queue, it might seem that it's the same as racing q1.receive and q2.receive, right? But that's not true because the race might actually end up evaluating both code blocks, right? And you might take off two values from the queues but only get one. So select actually fixes this problem and it will only ever receive a value from one channel that is read. And you can do quite nice things with it. One thing, for example, that's also possible is you can select from mixed. Again, quite a simple operation. Must be run within a scope. Starts a fork. In this fork, we select from these two channels, right? We can go to the implementation and you can see that it actually just repeats a select over and over again and propagates the errors. And then we can map into ways, right? Here we have map as view is like a map but without actually starting the fork, it's just create a view, so it's a small performance improvement. We can do a map par which will start up to 5 forks, which will perform mapping of the elements and then emit the elements in the order in which they were originally received. Quite useful when working with streaming data. Then we have some ways to discharge our streams, for example using for each. So we can build this high-level API on top of this streaming API. On top of these lower-level channels. Okay, so to jump to the summary. To sum up the good sides of the approach that we have seen, right? I think the concurrency approach is quite effortless. So we have those high-level methods that we can actually write to run things in parallel, to raise things. There's a number of other methods which you can actually come up with. We have quite familiar syntax, right? So we can just use plain old syntax as we did in the old times. We don't have to deal with monads, flat maps, and so on. We get meaningful stack traces. That's actually something that Project Loom gives us. It if there's an exception in the virtual thread, you will see the full trace where the invocations came from. We don't get any function coloring, right? So we don't have the virality of monads, which might be a good thing, it might be a bad thing, because you don't really know if code is going to suspend or not. But then you might say that whether code suspends or not might not be that interesting to track in the first place. So maybe there are more interesting things you want to track in your type system. We have supervision through structured concurrency. It is a bit also inspired, you can say, by Arca's let it crash, because once any fiber crashes, the whole scope will shut down, or the forks will be interrupted, and it will try to shut down at least. And finally, we've got channels, where you can use the low-level imperative interface, using .receive, using .send, which are blocking operations, using select, or you can use the high-level operations. There's also some bad sides, of course. We have seen that interruptions are inherited with Java's problems, right? It's actually possible to swallow an interrupted exception and to interrupt the interruption, you can say. The API with the lazy evaluation on demand with the binding parameters, it looks nice, but you know, it's you actually have to look into the method signature to see if it's lazy or not, right? With functional effect systems, everything is always lazy, so you know more or less what to expect. I didn't mention testing, but again, in functional effect systems, you can control the flow of time in your tests. We have seen resources which might be used unsafely, again, something that requires discipline. The channels need some performance work, so it's still an open question how fast they can get. The current implementation is more like a proof of concept, so it's quite slow. I did some investigations lately, and it can be made much faster, probably not as fast as, it depends on the number of stages that you define, so I'm not giving my final answer here yet. And finally, we've got refactoring, right? So we don't have referential transparency, which was mentioned in the first presentation, which might make refactoring a bit harder and a bit more fragile. Okay. The alternatives, which I think I already mentioned. So, of course, we've got features which we can use in Java, we can use them in Scala. We've got functional effect systems, such as Zio and Katz effect, which use a different approach, a different programming model, some downsides, some upsides. I actually tried to compare how these approaches I tried to compare these two approaches, and the result is a couple of talks and a couple of blogs. One that might be interesting is I tried to implement the Raft protocol, which is quite a concurrent one. I mean, it uses quite a lot of concurrency, using both Zio and JTK21. So the conclusions are similar to what we've seen here. And I also did a talk on last year's functional Scala about effects in general, comparing different effect systems, not only looking at concurrence but also at other properties. So maybe that will be interesting as well. Okay, and just to finish, I'd like to mention my company because of who I'm here, just so that you know what we do and what we might offer. So I work at SoftwareMill for actually, I think, 15 years now. That's quite a long time. We've been remote from day one, so I think we do remote quite well. Our specialization is in Scala, but we also do a lot of other things, mainly backends, various APIs, data processing, machine learning, not only Scala, but also quite a lot of Java, quite a lot of TypeScript on the front end, some DevOps. So if you would have, any business problem which you would like to flesh out in technical terms, we are there for you. Or if you would have any technical problem with Scala, Kafka, distributed systems, we are there for you as well. And we do quite a lot of open source, especially in Scala. So we've created the STTP project, which is a HTTP client. We created the tuple library, which is a way to describe endpoints and generate servers and clients and documentation from them. ElasticMQ, I think, is actually our most popular project, which implements SQS in a local environment, and a couple of others. So, as a summary, I think we have managed to avoid explicit concurrency, right? Because the best concurrency is that you can actually avoid doing it manually, right? You want to hide it. And I think we can actually quite often do it using the APIs that I have shown. Structured concurrency, I think, is a very nice approach, which allows you to understand what your code is doing, just looking by the source code, by looking at a single method, and by knowing that no threads will actually escape these scopes. And we have seen back-pressured channels inspired by Go. So the project, as I said, is open source. It's nowhere near being production ready, but you can try it out. We've got a Scala newsletter. If you're interested in Scala, you can subscribe. It's a weekly thing which arrives in your mailbox. Articles chosen by my coworker. If you have any questions further on, I'm on Twitter, Mastodon, Blue Sky, and if there's a new social network next week, I'll try to create an account there as well. Okay, and that's all I had. So maybe you have any questions. Yes?
Have you compared this approach to Kotlin's concurrency model?
Yes, so to coroutines.
Yeah.
Yeah. In coroutines, so the way coroutines work is that they do a compile time transformation into continuation passing style. So the first difference, of course, is that in Kotlin you've got function coloring, which isn't that different from iOS, like on the type level system, right? So they have the suspend functions, and in the Scala you have IOs. So that will be a downside on the Kotlin side, right? As far as performance goes, I did look at their channels, which are also they are also based on coroutines, and they have really good performance. I'm trying to replicate it in Project Loom, and it's quite close. Like I did only so far one type of test, and I'm trying to optimize this test as far as possible. It's actually quite close to what we can do with Kotlin. Kotlin has it a bit easier because, well, in the end, they compile down to something like what CasEffect does, meaning that you don't really have any stack which you have to save and then restore. But the functions return to the main loop, and then you can invoke the next one. So they have a little bit less overhead, but still Loom is quite performant and very, very close to coroutines, at least in these tests that I did, which were quite a few. So yeah, I guess that's as far as I got.
Is there an interaction with Java's low-level concurrency? I mean, for example, the synchronized and volatile keywords, right? For example, to be concrete, your channel implementation, it's some kind of queue using the synchronized blocks under the hood, right? There is no magic at this level.
Okay, no, the magic is quite constrained, yes. So first, maybe a note. So Project Loom did retrofit all blocking operations. Well, almost all blocking operations in Java. It didn't retrofit synchronized because there are some fundamental problems which I don't remember about right now. But if you do a synchronized block in Java in Project Loom, it will actually block the platform thread, which is not. So synchronized is, I think there are like 3 exceptions of things that you shouldn't do. It's synchronized, datagram sockets, and DNS lookouts, I think. which you shouldn't do, or which are blocking. And actually, this synchronize is the worst because for datagram and DNS, Java will start compensating threads which will try to take over the world. Anyway, in the implementation of channels, as I said, it's a very proof of concept type of implementation. But yes, it's based on concurrent queues, which you can find in Java, on atomic preferences, which are kind of volatile, better volatiles. But yes, it's all using Java's concurrency primitives.
Just to clarify, this project Loom, it is in Java 21. Is it like already, it's already there, or it's like a preview or something, no?
Yeah. So project Loom itself, it was published as a final part, like a publicly available feature of Java 21. The structured concurrency APIs, so the one that we have seen here, here at the top. So this API over here, that's actually in preview, so it will be stable like in the next LTS probably. But the virtual thread itself as a feature of the JVM is a publicly released thing. Okay, I guess pizzas are waiting, so we will wrap up. Thank you very much.